So, hi everybody. It's a great pleasure to give this presentation today after being involved in the organization of ISDA Online for quite some time. And so the talk will be about neighborhood verification and why neighborhood verification is actually a very useful tool for ensemble data assimilation and data assimilation in general to verify our systems. And before I start, I want to acknowledge the contributions by my co-authors. So especially Ludwig, Wolfgruber and Stefano, Serafin. This work originates from my time at the University of Vienna, but recently I moved to ECMWF. So if you want to reach out to ask questions, please use my new email address. It's provided here on the slide. And so we started looking into the fractional skill score for ensemble verification because we're interested in how we can verify ensemble data assimilation systems. And then we figured out there has not been much work in this direction. So we investigated it in more detail. And then we also found that surprisingly, the ensemble size dependence has something in common with this blue whale. So if you pay attention, you will notice this in the slides later on. So the objectives of my talk are the following. I will explain why you might be interested in using the fractional skill score. I will in detail explain how to compute the FSS for ensembles, and we'll spend quite some time to discuss the ensemble size dependence of different FSS approaches. And in the end, if there's some time, I will talk about the impact of ensemble size on forecast skill. So first of all, why using the fractional skill score? And if you go to the literature, you can find many studies that use the FSS to verify clouds like cell height gradients or precipitation, so radar information. So there are papers by Gier, Scheck, and recently Kugler et al. And so why do those studies? Why they decided to apply the FSS? So it allows to verify analysis and forecast fields that suffer from displacement errors. And what do I mean with displacement errors? So I decided to give this illustration here in the corner. So first of all, if you forecast a cloud, often the cloud does not appear in the forecast in the same location as in the observation. So if you would apply grid scale based verification methods and you have this displacement error here, you would actually get a double penalty error in the verification. Furthermore, you cannot really decide or distinguish whether the cloud had like a small displacement or a very large displacement. And actually in verification, you want to have like a method that can give you this information. So did my ensemble data assimilation system actually improve the positioning of the clouds or precipitation? And I decided also to show this example of precipitation here. So you can see that so this precipitation system was forecasted quite well by the ensemble mean forecast, but for the other cells, you have quite some displacement errors in the system. So so how does the FSS actually mitigate those displacement errors? And I wanted to show this nice diagram from the original paper on the FSS by Roberts and Lean from 2008. And so with the central grid point, you can actually see again this problem that in the radar, the precipitation was visible, but not in the forecast. And the idea is now not to do this grid scale based verification, but to introduce a neighborhood a convolution and then look at the fraction of the event, how often it occurred over this neighborhood. And you can actually see that if you look at the fraction, the forecast did a quite good job in matching the observations. And the question that I want to answer today is how can we use this neighborhood technique to actually verify ensembles? Because here it's not very clear and trivial what's the right approach to actually compare the ensemble with the radar observations. And as we saw, or as I mentioned earlier, in the literature there's a gap and there's not been like a very detailed evaluation of the ensemble size dependence of the FSS. So the questions that I'm going to tackle today are more or less the ones that we discussed in our preprint. This is already posted online. So I want to show you how the different ensemble-based FSS approaches that are or that have been proposed or that are possible behave with ensemble size and neighborhood size. Then I will spend some time on the probabilistic FSS. So that's one of the approaches that we think is the best way to evaluate ensembles. And I will discuss how this behaves with ensemble size and how we can predict its behavior. And I will spend some time on the dependence of forecast skill on ensemble size. So the data set that we're using is a convective scale 1000-member ensemble simulation. So some of you might know that the simulation originates from my PhD. And yeah, so we verify precipitation forecasts in a high impact weather period. In total, we have 10 forecasts that we verify at 4 valid times each. And yeah, for this study, we decided to make a perfect model assumption. So that this means we split our ensemble in 960 forecast member and 40 exchangeable random observation members. So this means we have synthetic observations to reduce like systematic biases between the forecast and the model. And for the subsampling, we decided to do a random subsampling without replacement. So this means for each ensemble size, we digest the same ensemble information. So if we look at the deterministic forecast, we actually have 960 forecasts, but if we verify a 40-member ensemble, we can only draw 40 independent, 24 independent 40-member ensembles. In total, we look at ensemble sizes ranging from a deterministic forecast to a 960-member ensemble. So how to compute the FSS for deterministic forecast to get us all on the same page? I want to briefly recall how this is done. So first, you have your forecast and observed field that you convert into a binary probability by using for precipitation a precipitation threshold. Let's say every precipitation event stronger than 1 millimeter. And then you get this binary probability field, and then you apply the neighborhood operation. So it's basically a moving window operation, a convolution, and then you get this neighborhood probability field both for the forecast and observation, which is like a field of a fraction of fractions. And then you can actually use those fractions to compute a mean squared error between the forecast and observation, which gives you the fractions prior score, which is like equivalent to the prior score. And yeah, if you want to compute a skill score, you always need to have a reference. And for the FSS, it's the maximum mismatch between the forecast and observation, which is also called the worst fractions prior score. And this can be used then to compute the FSS. And if you look at this formula and think about it, it becomes clear that 0 means no skill, and 1 means perfect skill. And yeah, as I mentioned earlier, when you compute the FSS, you have two free parameters. One is this threshold that you can choose, so the event that you're interested in. And the second one is the neighborhood size, so how much of the displacement area do you want to relax or account for in the computation of the FSS. Okay, so let's now discuss how can we account for the additional ensemble dimension in the computation of the FSS. And when you go to literature, we found 3 approaches. We added a fourth one. And the first one that has been used in literature is a quite obvious one. You simply replace the forecast field with the ensemble mean forecast. So instead of verifying a deterministic forecast, you just verify the ensemble mean and just keep the computation as it is. The second option is you compute an FSS for each member separately. So we get an ensemble of FSS values. So you can then also look at this person. So this is another approach that has been used in literature. One that hasn't been used it's a different type of ensemble pooling. We can also compute the fractions prior score and worst fraction prior score separately for each member, plug it into this equation, and then compute one FSS for the entire ensemble. And the last option is you can replace this neighborhood probability or the neighborhood fractions with a neighborhood ensemble probability. So what this means is you combine your ensemble probabilities with the neighborhood probabilities to derive like a combined probability field. And this is what we call the probabilistic FSS. So just on theoretical considerations, we already expect distinct behavior with ensemble neighborhood size for all those 4 approaches, because in the computation of the FSS, there are like non-linear operations involved, like the quotient or the thresholding. So let's now see if our expectations meet the results that we got from our data set. So let's start with the behavior with neighborhood size. So here you can see the FSS plotted as a function of the neighborhood size from a grid scale neighborhood to a neighborhood that matches the domain size. And you can see the behavior of all the 4 approaches that I introduced on the last slide. And the good thing is that all 4 approaches meet a theoretical expectation, because if we increase the neighborhood to the main size, the FSS simply measures the frequency bias of the event between the forecast and the observation. So the further we are away from 1 means that we have like a larger frequency bias of the event in the forecast compared to the observation.
3 minutes.
And this, oh, 2 minutes only, okay.
3.
And all FSS approaches follow this theoretical expectation, which is good. And yeah, so a small warning: if you want to use the FSS to diagnose skillful spatial scales, you need to be aware of this different behavior with the frequency bias. Okay, so now let's look at the FSS as a function of ensemble size. And here you can see that all 4 approaches behave substantially different. And yeah, first, let's go to the positive thing. They all converge to the same solution for the deterministic case. But if we look at the ensemble mean FSS, we see it has a very nonlinear behavior, and which is not optimal. So I would not recommend to verify the ensemble mean with the FSS. If you look at the average or aggregated FSS, so the different versions of ensemble pooling, we can see that it's almost constant with ensemble size. And if you look at this probabilistic FSS, we can see it increases with ensemble size, is well behaved and able to exploit probabilistic information. So the good thing is I would suggest to use the PFSS, because this has really some good properties and is able to like show the improvement in skill that you get from using a large ensemble. And as we saw in our study and found, is that it's very similar to the Breyer skill score that's well known and applied. And yeah, I now want to spend some time to talk about this ensemble size dependence that you can see here. So when we tried to find the equation that matches or describes the ensemble size dependence, we actually started with an empirical approach and fitted the data from our ensemble. And in the end, we found that our equation that we find is very similar to a known result for the Breyer skill score. And the only thing that we needed to change is we needed to introduce this alpha parameter, which is like a slope parameter, that the equation can actually very well match our data. And so the great thing is we can now use this formula and reformulate it in a way that we get an equation for the probabilistic FSS of an infinite large ensemble. And this is a very good thing, because then the PFSS infinity can be used as a fair score. So you can basically compare differently sized ensemble systems in a fair way. And yeah, so we empirically estimated this slope parameter alpha. And this is the distribution of alpha values that we get for all our cases that we evaluated. So different lines show different frequencies of the forecasted event. And in blue, you can see highlighted like the 5% most extreme precipitation events. And the different whiskers show different neighborhood sizes. So this means for the like a grid scale neighborhood, you should choose like an alpha that's about 0.75, but while you move to larger neighborhoods, you can choose an alpha that's closer to 1. And yeah, to draw the line to the beginning of my talk, this is where you can see that actually the alpha values resemble the shape of a blue whale. In my opinion, I think it's a nice analogy to kind of recall the ensemble size dependence. And with that, yeah, I want to conclude. So how do different ensemble-based approaches behave with neighborhoods? So the good thing is all approaches follow the theoretical expectation, but exhibit distinct frequency biases. Their behavior with ensemble size was very different. So if you computed the FSS in the past from ensemble, check which approach you used and make sure that you keep this in mind when comparing different ensemble systems. If you haven't used the FSS before and want to use it, I would suggest to use the probabilistic FSS for ensemble verification, because it's well behaved and can really use the probabilistic information and has strong similarities to the Breyer skill score. And yeah, I would suggest to use the PFS and the proposed formulas for ensemble size correction. And yeah, I will use it in the future to verify clouds and precipitation at ISDA. So yeah, if you're interested and want to learn more, we have even more results in our preprint. Just go to Authoria and follow the door. And with that, I want to thank you, and I'm open for questions.
Yeah, thank you very much, Tobias, for this very nice, yeah, also over explanation of this important method and your extension to ensembles, which I think is also very important. We have maybe time for a very quick question left. I don't see any, but I would have a question. Could you, I mean, with different, the different scores measure different things. When you when you try to when you use scores, you want to know something about the quality of your forecast. Could you say what a priori, apart from your scaling considerations, which score would you prefer a priori, so to say, to if you have your ensemble and you want to know how good is it?
Yeah, so this is a good question. So I think the answer always is you should never trust one score, but apply a variety of scores to get like a good understanding of what's going on in the ensemble. And as I mentioned initially, like if you really are interested in clouds and precipitation, you need to be aware that often like clouds and precipitation are diagnosed quantities, so no prognostic model variables. So you cannot expect that they overlap at the grid scale. So it's very important to like kind of use neighborhood methods that can accommodate for this property. And I would really try to use 3 or 4 like verification methods and not only look at one to get like a good understanding of the ensemble.
I mean, which of the 4 fraction skill score versions?
So I would really use the probabilistic FSS. Yeah. So because it's very similar to the Breyer skill score and it's very good properties. Yeah.
Okay, thank you. There's actually one question in the chat. It's Daisuke Hochhotter. He asks, says, very nice talk, thank you. In page 9, would it be possible to replace binary probability with number of members exceeding criteria, divided by ensemble size, to define yet another ensemble version of fractions of the FSS?
Yes, this could actually be another approach to do it. I haven't thought about it. I will consider it. So thanks, Daisuke, for the comment. But yeah, this would be another option. Yeah.
Okay. Yeah. Thank you, Tobias, again. I think we have to go on.